Imagine throwing your most cherished possession, a diary filled with your life's memories, a unique painting, a rare coin, into a black hole. What happens to its story, its unique details, its very essence? Does it vanish forever, erased from existence without a trace? Or is its information, its quantum fingerprint, somehow preserved, perhaps transformed beyond recognition? This isn't just a philosophical thought experiment. It's one of the most profound and puzzling mysteries in all of physics, the black hole information paradox. For decades, scientists have grappled with this cosmic riddle, a problem that strikes at the very heart of how we understand the universe. It pits two of our most successful theories, Einstein's general relativity, which describes gravity and the large-scale structure of spacetime, against quantum mechanics, which governs the tiny, fundamental particles that make up everything. Both theories are incredibly accurate in their own domains, but when they meet at the extreme edge of a black hole, they clash, presenting us with a contradiction we simply cannot resolve. This isn't a minor detail, it's a fundamental conflict that highlights a deep crack in our understanding of reality. First, let's understand the black hole itself. General relativity tells us that a black hole is a region of spacetime where gravity is so intense that nothing, not even light, can escape. It's defined by a boundary called the event horizon, a point of no return. Once you cross it, you're on a one-way trip to the singularity at the center. From the outside, a black hole is surprisingly simple. It's often described as having no hair, meaning it only cares about three basic properties: its total mass, its electric charge, and how fast it's spinning. It doesn't remember what it swallowed, whether it was a star, a planet, or your diary. It just incorporates that mass, charge, and spin into itself, outwardly appearing the same regardless of what went in. Now let's talk about information. In physics, this isn't just data or facts, it's a very precise concept. It refers to the unique quantum state of every single particle, its position, its momentum, its spin, its energy, and all the intricate relationships between particles. Quantum mechanics, our best theory for the very small, has a fundamental rule: information can never be truly lost or destroyed. It can be scrambled, mixed up, and hidden, but in principle, it can always be recovered. Think of burning a book. The pages turn to ash and smoke, but the atoms and energy are still there. If you could precisely track every single particle, every photon and electron, you could, theoretically, reconstruct that book down to its original words. Information is conserved. But in the 1970s, Stephen Hawking introduced a game-changing idea. He showed that black holes aren't perfectly black. Due to bizarre quantum effects near the event horizon, they actually glow. This is called Hawking radiation. Imagine empty space as not truly empty, but constantly bubbling with virtual particles, pairs of particles and antiparticles that spontaneously pop into existence, briefly interact, and then annihilate each other. Near a black hole's event horizon, one half of such a pair might fall into the black hole, while its partner escapes into space. The escaping particle carries away a tiny bit of energy, which, according to Einstein's famous equation E equals mc2, means it also carries away a tiny bit of mass from the black hole. Over an incredibly long time, black holes slowly shrink, radiating away their mass, until eventually they evaporate completely, vanishing into nothingness. This radiation is predicted to be extremely faint, far too weak for our current telescopes to detect, but the theory is robust. Here's where the paradox truly hits. Hawking's calculations suggested that this radiation is purely thermal, like the random heat given off by a hot stove, not encoding any specific details about what fell in. It's generic, universal, depending only on the black hole's mass, charge, and spin. So if a black hole forms, swallows your diary, and then slowly evaporates, emitting only this random, thermal radiation, where did the unique quantum information of your diary go? If it's not in the radiation, and the black hole itself is gone, then the information seems to be truly destroyed. This directly contradicts the fundamental principle of information conservation, from quantum mechanics. We have a universe where information is conserved everywhere else, but seemingly lost forever inside a black hole. This is the black hole information paradox, a direct, head-on collision between general relativity and quantum mechanics. Scientists have proposed several ambitious, yet unproven, solutions to this profound puzzle, each with its own set of challenges. One idea, initially favored by Stephen Hawking himself, was that information really is destroyed. This would mean quantum mechanics is incomplete or breaks down in the extreme gravitational environment of a black hole. However, this is a very difficult pill for most physicists to swallow, as it would imply a fundamental flaw in one of our most successful theories and could have unsettling implications for the predictability of the universe. Hawking eventually reversed his position, suggesting another path. Another leading hypothesis suggests that information does escape, but in an incredibly subtle way. Perhaps Hawking radiation isn't perfectly thermal and random. Instead, it might contain incredibly complex, entangled correlations, like a cosmic barcode, that subtly encode all the information about what fell into the black hole. Imagine listening to static, but within that static, there's an impossibly faint, scrambled message that holds every detail of every atom the black hole ever consumed. The challenge here is how this information could possibly be encoded and escape without violating other fundamental principles of quantum mechanics, like the no-cloning theorem, which states that information cannot be perfectly duplicated. Some ideas, like fuzzballs from string theory, propose that black holes aren't true singularities, but rather diffuse, fuzzy objects, and information never truly crosses an event horizon, but is instead stored on its surface. A third possibility is that information is never truly lost, but instead remains stored in a tiny, stable remnant after the black hole has finished evaporating. This remnant would be an unimaginably dense object, perhaps no larger than a Planck length, the smallest possible unit of space, but it would somehow contain all the information of everything the black hole ever absorbed. The major problem with this idea is figuring out what such a remnant would be made of, how it could remain stable, and how such an infinitely tiny object could possibly store an infinite amount of information without violating known laws of physics. The black hole information paradox remains one of the most exciting and frustrating unsolved mysteries in physics. It forces us to confront the limits of our current understanding, showing us that our two most successful theories, general relativity and quantum mechanics, are fundamentally incompatible in this extreme cosmic arena. Solving this paradox wouldn't just be an answer to a peculiar question about black holes. It would likely reveal a deeper, more unified theory of quantum gravity, connecting the fabric of spacetime with the quantum realm. It's a humbling reminder that even with all our progress, the universe still holds profound secrets, waiting for us to unravel them. If you're as fascinated by these cosmic puzzles as we are, consider subscribing for more journeys to the edge of human knowledge.